Hey there. Welcome to our channel. We're so glad you're here. Please like, share, and subscribe to join us for awesome content. Also share this video with your family and friends. Let's get started. Imagine the universe as a vast, quiet kitchen. Stars simmer like stovetops, and around them, planets swirl in slow, steady orbits. Some too close to the heat, some too far away. But here and there, a world lingers in the perfect in-between, where conditions are just warm enough, just gentle enough, for liquid water to pool and cling. Astronomers call this the Goldilocks zone, the region around a star where a planet could, in theory, cradle life as we know it. Not too hot, not too cold. Just right. Yet this idea is softer, stranger than it seems. Because life, as Earth whispers to us, is stubborn. It thrives in boiling vents under the ocean, in Antarctic ice, in deserts where rain falls once a decade. So why do we search for this just right place? Because water, that humble, shimmering molecule, is the closest thing we have to a universal rule. Where it flows, life might follow. Not all stars are equal. A small, cool red dwarf cradles its planets close, like a campfire gathering huddled figures. A massive blue giant burns so fiercely that its Goldilocks zone is pushed far out, a distant ring where worlds might drift in lonely orbits. Our sun, that golden middle child, offers a temperate belt where Earth has basked for billions of years. But even here, the rules bend. Venus sits just inside our sun's habitable zone. Yet its thick air chokes with heat, a warning that location alone isn't enough. Mars lingers at the outer edge, its thin atmosphere whispering of lost oceans. The lesson? A planet's story isn't written by starlight alone. It's also written by air, by rock, by time. Now let your mind wander further. What if just right isn't about sunlight at all? Far beyond the traditional Goldilocks zone, frozen moons like Europa and Enceladus hide oceans beneath their ice, warmed not by their distant sun, but by the slow, gravitational kneading of their parent planets. These are the snowball worlds with beating hearts, where life might exist in slow, dark tides. And then there are rogue planets, orphaned worlds flung from their stars, drifting through the black. Could some of them, wrapped in thick blankets of hydrogen, keep underground seas warm for eons? The universe, it seems, has more recipes for life than we've yet imagined. So as you settle into the quiet tonight, let the old idea of the Goldilocks zone soften at the edges. The universe is not so simple. Habitability is not just a matter of place, but of time, chemistry, and hidden, patient warmth. And if that's true, what waits beneath the ice? The ice that breathes frozen shells with hidden hearts. Picture this. You stand on an endless plain of ice, smooth as glass, stretching farther than any horizon you've ever seen. The sky above is black, starless. Your sun is just another faint speck in the distance, too weak to melt even the thinnest frost. Beneath your feet, though, something extraordinary hums. Down, down, through miles of frozen crust, an ocean waits. Not a frozen wasteland, but a dark, swirling sea, kept liquid by the slow heartbeat of the world itself. This is Europa, Enceladus, Ganymede. Moons that should be barren, but instead hide secret oceans deeper than Earth's own Mariana Trench. How does water stay liquid so far from the sun? The answer lies in tides. Not the gentle lapping of shores you know, but a vast gravitational embrace. Jupiter, Saturn, these gas giants are cosmic puppeteers. Their immense gravity tugs on their moons, stretching and squeezing them like clay in a potter's hands. This constant flexing creates friction deep inside, warming the rock below the ice, melting it just enough to form vast, hidden seas. Think of it like kneading dough. Each press of your palms generates warmth. Now imagine that same motion, but on a planetary scale, happening for billions of years. That heat doesn't fade. It lingers, trapped beneath the ice. A submerged furnace keeping the water liquid in eternal night. If life exists here, it would move to a different rhythm. No sunrises, no seasons, just the slow, steady pulse of geothermal heat. On Earth, we find microbes thriving near volcanic vents at the bottom of our oceans, feeding not on sunlight, but on chemicals. Chemosynthesis, it's called, a way of life that needs no light, only minerals and warmth. Could the same happen here? Perhaps. These alien oceans might host their own dark reefs. Not coral, but delicate filaments of bacteria, clinging to vents where heat seeps through the seafloor. Their metabolisms would be slow, their lifespans long. A single cell might live for centuries, growing, dividing, dying at a pace we can barely fathom. Sometimes, these hidden oceans betray their presence. Loving this? Hit that subscribe button to keep up with our videos. Also share this video with your family and friends. On Enceladus, geysers of water erupt from cracks in the ice, spraying into space like a sigh held too long. Europa's surface is scarred with jagged ridges, where the ice has fractured and refrozen over millennia. If you listen closely with the right instruments, you might even hear these worlds whispering. The creak of shifting ice, the groan of water forcing its way up through fissures. These are the sounds of a world alive beneath its shell. So as you close your eyes tonight, imagine it. A place where the sky is solid, where the only light comes from the glow of minerals in the deep, where life, if it exists, has never known a sunbeam, only the slow, steady warmth of a planet's hidden heart. And if life can thrive there, what other dances might it perform when the music is written by gravity alone? Close your eyes and imagine the slowest dance in the universe. Two partners, a massive planet and its small moon, locked in an eternal embrace. With each orbit, invisible threads of gravity pull between them, stretching their shapes ever so slightly. This is the tide's beginning. Not just waves on a shore, but whole worlds breathing in and out. On Earth, we see this as our oceans rising and falling. But on icy moons like Europa, this dance happens in extreme slow motion. The ice shell flexes. The hidden ocean beneath churns. Fissures open and close like lungs taking a breath that lasts for days. Beneath the ice, these tidal forces create something extraordinary. A perpetual motion machine powered by gravity. As the moon tugs, the ocean beneath responds. Water slides against rock, creating friction, generating warmth. These are currents that never see sunlight, yet may carry the building blocks of life across entire worlds. Picture Earth's Gulf Stream, but moving in complete darkness. Warm water rises near hydrothermal vents, then travels thousands of miles before cooling and sinking again. A single loop might take centuries. Any potential microbes in these waters would surf these slow waves, drifting through a journey that spans generations. The surface tells the story of this constant flexing. Europa's frozen crust is crisscrossed with lines. Not random cracks, but a precise record of gravitational conversation. Some ridges stand taller than mountains, formed over millennia as ice grinds against ice. If you could press your ear to Europa's surface and survive the -160 degrees Celsius cold, you might hear it. The deep groans of shifting ice, the pops of gas escaping newly formed fractures. These are the sounds of a living world, not biological life, but the constant geological murmur of a moon responding to its partner's pull. This tidal energy does something remarkable. It creates stability in the darkness. While surface conditions on planets can change dramatically, storms, seasons, ice ages, these subsurface oceans may have remained liquid for billions of years. The heat source never falters. The dance never stops. It's possible that life here wouldn't just survive, but synchronize itself to these rhythms. Reproductive cycles might align with tidal stresses. Migration patterns could follow the slow pulse of currents. An entire biosphere might exist on a timescale we can barely perceive, where a single lifetime spans millennia. As sleep draws nearer, let your mind drift with these hidden tides. Imagine being a single microbe in that vast dark ocean, carried by currents you don't understand, nourished by warmth from below rather than light from above. Your entire universe is the push and pull between a moon and its planet, a relationship written in gravity and answered in water. Imagine a world without light, not just the absence of day, but complete, perpetual blackness, where photosynthesis never evolved because photons never arrived. Here, life would need a different currency. Not sunlight, but substance. On Earth, in the crushing depths of our oceans, we find the blueprint for such existence. hydrothermal vents. These are not like undersea volcanoes, but chimneys of minerals, pumping out warmth and chemicals into the freezing dark. Around them, entire ecosystems thrive without a single drop of sunlight. The secret? Chemosynthesis, a way of harvesting energy not from light, but from molecules. Hydrogen sulfide, methane, iron compounds. These become the food for bacteria, which in turn feed entire communities of tubeworms, clams, and blind shrimp. Now take that concept and stretch it across geological time. In Europa's ocean, where tidal heat is gentle and constant, life might operate in ultra-slow motion. A microbe here might take a year to complete a single division. Its enzymes would work at temperatures barely above freezing, chemical reactions creeping along like sap down a tree in winter. 1,000 Earth years could pass between generations. Why rush? In an environment where energy is scarce but stable, the winning strategy might be patience. Life here wouldn't burn energy, it would preserve it, like embers banked in a hearth meant to last for centuries. If such life exists, how would we know? Perhaps by detecting unexpected chemical imbalances, too much hydrogen where there should be none, or strange ratios of isotopes that hint at biological sorting. Or perhaps we'd find macroscopic signs. Fields of delicate, glass-like structures growing around vents, their forms too regular to be geology. Maybe even fossilized patterns in ice cores, showing that something once moved, fed, lived beneath the frozen crust. As sleep pulls at your mind, consider this. The chemistry of life may be far more flexible than we ever imagined. On Earth, we're carbon-based, water-breathing, sunlight-chasing creatures. But out there in the dark, life might have written its own rules, using the same atoms, but composing an entirely different song. And if life can rewrite its own chemical score, what melodies might we hear if we finally listen to those frozen worlds properly? Imagine a world that inhales and exhales on geological timescales. With each cosmic breath, ice creeps forward like a slow tide, encasing continents in frozen armor. Then, millennia later, the glaciers retreat, liquefying, evaporating, revealing liquid seas once more. These are cryo-worlds, planets caught in a cycle of deep freeze and rebirth. Some may orbit variable stars that dim and brighten over millions of years. Others might experience extreme axial tilts, plunging hemispheres into prolonged winters that last for ages. The question isn't just whether life could survive here, but whether it could pause itself entirely, waiting out the cold in perfect stillness. Now stretch that endurance across millions of years. Imagine microbes with cellular structures that crystallize neatly rather than rupture, their metabolism dialed down to near zero. Not dead, just dormant like a computer in sleep mode, preserving the last vital lines of code until power returns. The first organisms to wake might be the simplest, chemosynthetic bacteria reactivating vents, rebuilding the base of a food web. More complex creatures could follow, emerging from icy crypts like characters in a frozen fairy tale. Some cryo-worlds might never fully wake. Their thaws could be brief, just long enough for life to reproduce once before the next freeze. In these cases, evolution would move glacially, with each generation separated by epochs of stasis. As you drift towards sleep, consider this. The universe operates on timescales we can barely comprehend. A microbe that wakes once every million years experiences time differently than we do. Its life might be a series of brief, bright moments separated by darkness, like a firefly flashing in the night. And if life can persist through such unimaginable pauses, what does that say about its tenacity across the cosmos? Picture standing on a plane of ice, but not the brittle, cracking sort you know. This ice bends under its own weight, flowing like chilled syrup. Each step would leave a footprint that slowly fills in behind you, the surface healing itself in hours or days. This is high-pressure ice, a substance that behaves differently from anything in your freezer. At depths found in subsurface oceans or on massive exoplanets, ordinary H2O transforms. The molecules pack tighter, forming exotic crystal structures. Ice 2, Ice 6, Ice 7, each with its own strange properties. Some of these ices remain solid at temperatures that would boil water on Earth's surface. On a world like Ganymede, Where pressures reach 100,000 times Earth's atmosphere, ice behaves in impossible ways. These properties create environments where water never fully solidifies, where thin films of liquid persist between ice grains, forming a labyrinth of microscopic tunnels. It's in these spaces, some no wider than a single water molecule, that the building blocks of life might find sanctuary. Amino acids could link together on ice surfaces like beads on a string. Lipid molecules might form primitive membranes along liquid channels. Their metabolism would be measured in geological time. A single cellular division might take decades. But in an environment where change itself is slow, this could be the perfect pace. As your breathing deepens, consider this paradox. The same crushing pressures that would destroy life as we know it might create the perfect conditions for life we've yet to imagine. In the universe's silent laboratories, under ice that shouldn't flow and in cold that should preserve, the rules rewrite themselves. And if life can emerge in these impossible interstices, what other paradoxes might it solve in the darkness? Picture yourself standing on a plain of frozen nitrogen. The ground beneath your feet isn't rock. It's a slab of ice so cold it flows like glacier over millennia. The sky hangs pale and thin, scattering sunlight into a perpetual twilight. In the distance, mountains of water ice rise like sentinels, their peaks dusted with methane snow that evaporates directly into the thin atmosphere when the weak sun touches them. This is Pluto, not the frozen dead world we once imagined, but a dynamic ice machine operating in ultra-slow motion. Some of Pluto's most striking features are its methane dunes, frozen waves stretching across the Sputnik Planitia ice plain. These shouldn't exist. Pluto's atmosphere is too thin to create wind strong enough to move sand. Yet there they stand. The solution: seasonal sublimation. As methane ice turns directly to gas, it provides just enough push to send grains tumbling. This reveals a world where landscapes form not through steady processes, but in sudden, delicate bursts of activity, separated by centuries of stillness. As you drift off, consider this. On Pluto, the very definition of environment changes. Weather happens once per human civilization. Rivers flow, but their water is rock-hard ice. The chemistry of life, if it exists, would be written in elements we usually consider waste gases. And if life can adapt to such alien rhythms, what might flourish when we look beyond frozen worlds to those where the ice never melts at all? And if life can adapt to such alien rhythms, what might flourish when we look beyond frozen worlds to those where the ice never melts at all? Imagine trying to read a book by candlelight from 10 miles away. This is the challenge astronomers face when studying exoplanets. The signals are faint, buried in noise, written in light's subtle vocabulary. For ice worlds, the clues are even more elusive. Their cold surfaces reflect little light. Their atmospheres, if they have any, are thin and still. We must become cosmic detectives, searching for absence as much as presence. Every substance has a light fingerprint. Water ice absorbs specific infrared wavelengths, creating tiny valleys in a planet's reflected light spectrum. Advanced telescopes like JWST look for these telltale dips, but the signatures of frozen worlds are subtle. The most exciting find would be spectral contradictions, places where the chemistry doesn't match what geology alone could produce. On Earth, we know life by its thermodynamic signature. It creates chemical imbalances. An atmosphere with both methane and oxygen shouldn't exist unless something is constantly replenishing them. For ice worlds, we look for similar paradoxes. The Europa Clipper mission will use its SUDA instrument to analyze ice grains ejected from the moon's surface, searching for these biological hints. Sometimes the most telling data comes not from light, but from motion. The libration of icy moons, tiny orbital wobbles, can reveal subsurface oceans. Europa's surface shifts up to 30 meters during its orbit, like a water balloon gently squeezed. Future missions may detect even subtler movements, the microtremors of ice cracking, or tidal flexing in real time. These could map the hidden plumbing of icy worlds. The challenge multiplies for exoplanets. By the time light reaches us from TRAPPIST-1's frozen worlds, 39 light-years away, it's been stretched, scattered, and diluted. We're reconstructing entire planets from photons that could fit on a pinhead. Each finding is like hearing one note of a symphony, we must learn the rest by implication. As sleep draws near, consider this: the universe is constantly broadcasting. In neutrino fluxes, in gravitational waves, in polarized light, every planet tells its story. We're just beginning to learn the language. And if we do find life's signature in these frozen whispers, how will its discovery change what it means to be alone? Beneath Antarctica's glaciers, where temperatures plunge to -60 degrees Celsius and darkness reigns supreme, life persists in the unlikeliest places. These organisms don't merely survive the ice, they harness it. Some use ice crystals as scaffolding for their colonies. Others produce antifreeze proteins that carve liquid veins through the frozen matrix. Their existence proves that where there's water, even locked in ice, life finds a way. Psychrophiles, cold-loving organisms, operate on biological principles that seem alien. A single bacterial division might take months in permafrost. Yet these organisms complete the full dance of life, just in ultra-slow motion, like a ballet performed at quarter speed. When we study Earth's ice dwellers, we're peering through a fractal mirror, each discovery reflecting possibilities for alien life. These creatures are a Rosetta Stone for decoding extraterrestrial biology. This reveals an astonishing truth. Cryptobiosis, the ability to enter suspended animation, may be a universal biological strategy. On worlds with intermittent habitable periods, life might sleep for eons between awakenings. As you drift towards sleep, consider this: every time we've declared life can't exist here, Earth's extremophiles have proven us wrong. The boundary between possible and impossible shifts with each discovery. The frozen microbes whispering beneath our feet are teaching us to think differently about frozen worlds light years away. Their quiet resilience suggests that life may be less fragile and more ingenious than we ever imagined. And if Earth's simplest organisms can rewrite the rules of existence, what might evolution accomplish given billions more years and a galaxy of frozen worlds to explore? Picture this moment from a distant star's perspective. You lie wrapped in darkness, breathing steadily as Earth turns beneath you. Somewhere above, the ice moons of Jupiter glide through their orbits. Europa's frozen crust straining over its hidden sea. Ganymede's magnetic fields weaving invisible patterns in space. These worlds have existed for billions of years without witnesses. Yet tonight, your thoughts brush against them. For the first time in cosmic history, the universe has grown aware of itself through you. All the ingredients we've explored distill to a simple truth. Water plus energy plus time equals possibility. The universe has experimented with these combinations for 13.8 billion years. That we exist proves the formula works, but we may be just one version of the solution. Now reverse the perspective. What if we're the ones in the enclosed system? What unseen boundaries contain us? We search for life because we're lonely. Yet the more we learn, the stranger that loneliness becomes. We're already made of the universe. Finding life elsewhere would simply be recognizing ourselves in another form. Let your final waking thoughts be these. Somewhere tonight, on an ice-encased moon, in a methane sea, beneath glaciers that flow like honey, molecules may be arranging themselves in patterns we'd call alive. The universe is dreaming in countless ways. And you, curled in your bed on this pale blue dot, are one of its most beautiful dreams. Awake just long enough to wonder about the others. Sleep now. The stars will keep watch. Thanks for watching. Please subscribe, like, and share. See you next time.